My name is Nathan Coffield. I'm here to talk about how to design a high availability solution for MySQL using Python. So in 2010, when I moved to the Valley, there was no real out-of-the-box solution for MySQL failover. I joined the Facebook site reliability operations team, and we were like doing failover by hand. It was cumbersome, prone to human error, and resulted in extended downtime for our users. Even today, group replication is not widely adopted as a failover solution. So in this talk, I'll walk you through the thinking that allowed us to design a system for detecting and remediating MySQL primary failures using Python automatically. Full deep dive on this topic takes typically about an hour. So I'll do my best to get you up to speed in the next 20 minutes. That means I have about 90 seconds per slide. So wish me luck. So just a brief agenda. First, we'll take a look at how a typical load balancer handles a failure in a stateful service. Afterwards, we'll attempt to use that same concepts to implement our failover system for MySQL. I'll show you some example Python that can detect a failure and dive a bit deeper into the limitations of that solution. After we address those limitations, I'll briefly describe the process for demoting a primary server, and then we can get on with the Q&A. At the end of the slide, you'll find links to my Lightning Talk at Box, which elaborates a bit more on the MySQL specific details, and presentation from my friend Jeff Zhang from Percona Live, which goes into much greater detail into these systems. Finally, I'll provide my contact information if you'd like to follow up offline with more questions. All right, so this first slide represents the typical load balancer. We have several nodes, which all serve the same content. The load balancer typically has some method to validate the status of those nodes. In this example, the first two nodes are obviously healthy, but our third node is experiencing a failure. The load balancer now knows that it should not serve any additional requests through that connection. Additionally, we have a third column here which can help determine the load on a given node. Typically, you might have some maximum number of connections your web server can handle, and the load balancer will do its best to equitably distribute load amongst the group. Let's see the same data structure. Let's see if this same data structure can be used for MySQL. In this diagram, we try to map the concept of a stateless load balancer to MySQL concepts. In the first columns are members of a replication group. DB1 and DB2 are both replicating from DB3 and should have an exact copy of the data, which is only slightly behind the primary. We aren't doing any fancy multi-master replication here. All writes have to go to DB3 before arriving at DB1 or DB2. MySQL has a concept of an IO thread. So we can use the SQL commands using the MySQL protocol to query the status of the replication thread. No such command exists for the primary replica since it's not replicating, but we can use a select one as a fairly reliable status check. Third column represents latency of the replicas relative to the primary instance. This will allow us to disable a replica if for any reason it begins to lag past our application's latency thresholds. Obviously, the primary instance has no replication lag because that's where the writes originate. So now we know we should be able to get the necessary information to determine if a replica or the primary is offline. In order to implement our failover system, we're going to need some shared topology server to distribute members of the nodes of the group and tell us who the primary is. In a load balancer, nodes might be hard-coded into the configuration, but for DB connections, we typically store these details in some kind of service like Zookeeper or Console. If we can't query for the IO status, a replica is offline. If the IO thread status is non-zero, we know that the replica is online, but the connection to its primary is unhealthy, potentially indicating a primary failure. Unlike the stateless service, clients are not served directly through a load balancer. An application needs to be routed to the primary for writes and the closest replicas for read queries. We'll need some kind of algorithm to ensure that a single unhealthy replica does not cause us to assume the primary is offline. So The following is just pseudocode. It's the fewest lines of code I could come up with to adequately describe this process. And I apologize that you cannot copy and paste this and have a failover system. Every replica in the group would run this script as a sidecar alongside the MySQL process. Lines 4 to 8 implement our status checks we described in the earlier slide. It's pretty straightforward. Select one on the primary and show slave status for replicas. In this way, we can collect the status information we'll need for failover. Lines 12 and 20 is where we obtain consensus, and that's really where all the magic is happening. We use a thread pool to talk to every replica in the group, and on line 20, we collect those results. And if more than half of our replicas concur that the primary is offline, we'll return false. This ensures that all members of the group, or at least a majority, agree that the primary is offline, and we can do our failover. So in the main thread there, in the main function there, you see we're just in a constant while loop. If the primary goes offline, we're going to demote it. This solution has some problems. This is essentially what we had at Facebook in about 2013 when I joined the DBA team, and we needed to address some of the problems. Using IO thread status, we can only verify the link state between the primary and the replica, but you can't detect a disk failure, which can be worse than a network failure. Also note, I didn't show the process to disable a replica in the previous script, but it's pretty simple. If the replica is offline or seconds behind math sure exceeds our threshold for latency, we disable the replica from the primary. Our failover system should ensure that a primary is online to perform that operation. Unfortunately, there's no way to verify the write path using the MySQL protocol alone. You cannot make a replica write to a primary. And so we would need to create our own protocol to transfer this data between our agents. If we go back to our previous data structure, we can solve the write path problem by performing a heartbeat insert from our script. And we'll create an internal table for that purpose. So essentially, we just create a heartbeat table. To determine if our heartbeat inserts were successful, we'll need our scripts to be able to talk to one another. So we'll implement a server which can do just that. At Facebook, we use Thrift for this purpose, but gRPC and Protobus can do the same thing. We'll create the thread to perform the inserts and gather status from members of the group. And we'll write a Demoter thread that will perform our consensus check when we detect a local heartbeat failure. Here you can see our status query has changed from a read-only query to a query which writes into our new heartbeat table. This will be used by the local agent to get its own view of the write path. The get status function has been changed to connect to our status service to get the result of the remote replica's heartbeat inserts. Finally, we iterate through our group members, collecting the appropriate status metadata, just like we did before. And that's basically the status thread. We'll also need something that's going to, now that we've collected the necessary status data, we can once again determine consensus. So in this example, we initiate a quorum vote if the local status thread failed its own heartbeat insert. Again, if more than half of the replicas agree that the primary is offline, we can initiate a demotion. We also need to implement get primary status so our peers can see the result of our own heartbeat inserts. And so that's what you see on line 45. I went a lot faster than I expected. So how do we demote a replica? You may not be familiar with MySQL, or it kind of just seems kind of hand wavy. I didn't cover this in the pseudocode because it'd be a pretty involved process, but the gist of it is that we need to find the replica with the latest transaction, ensure those transactions are replicated to other members of the group, and then, if necessary, promote to a replica in a preferred region, one with the lowest latency relative to our applications. Once all this is complete, we can change the topology service to point to the new primary. I did it in 10 minutes. So here you'll find the links to some of the public talks we've given on this topic in the past. I'll include this link in the chat for you guys, both the Slack and the Remo chat. there's a lightning talk we did at Box and the talk for Percona Live. The slides there have much more in-depth coverage about how all this works and what various systems need to interact in order to make sure that this is safe and performant. Finally, I have a link here for MySQL group replication so that hopefully you don't have to implement your own failover system. If you're using MySQL 5.7 or 8.0, you should be able to get away with just using group replication. Finally, here's some of my contact info if you'd like to talk